And to do that, we're going to discuss permutations and combinations. So permutations and combinations are probably things that you've heard of. Maybe you've seen formulas for these in other classes. But the big ideas here are going to be permutation, which we will sometimes call PNR, and combination, which we will sometimes call CNR, although I dislike this notation. I prefer the notation N choose R. And we'll also briefly look at double counting, just as a general counting strategy. So, what is a permutation? Well, a permutation. So a permutation. Permutations are ordered lists of R objects chosen from N. It's permutations. Combinations are unordered lists of R objects chosen from N. So permutation is going to be something like, you know, a list of things where the order matters. So, you know, maybe the order of chapters in a book or the order of songs in a playlist, where the order matters if the playlist isn't played on shuffle. An unordered list is going to be something like a grocery list, right? If my wife puts something on the grocery list for me to buy at the store, she's probably not going to specify in what order I put it into the cart, right? She's not going to be like, no, make sure you grab the cheese before you grab the lettuce. You wouldn't want the cheese to sit on the lettuce. Wouldn't want to have lettuce cheese. Right, so combinations is going to be when the order does not matter. So it's an unordered list. So let's do two quick examples. So 10 horses run a race. I've got two questions. A, how many ways can the top 3 medals be given out? And B, how many different triples can receive the top 3 medals? And let me emphasize, triples is just a group of 3. So let's just emphasize unordered. Okay, well, for part A, I've got to choose 3 horses from the 10, and a horse can't finish first and second, right? So there's going to be no repeats. So to choose the first, second, and third place horses, I'm going to have 10 choices for the first, and so times 9 choices for the second, and times 8 choices for the third. All right? And I really prefer the answer to be like this. You could write 720. That's fine. But I really prefer that answer. Now for part B, I'm asking for less information, so I have to work harder, which is a little paradoxical. What I have to do is, well, I've got 10 choices for first place, times 9 choices for second place, times 8 choices for third place, but then I need to divide by the number of ways to order those. You remember from the symmetry rule, from the section before pigeonholing, if I have these list of the top 3 horses, then I've got, let's say the horses are A through whatever the 10th letter of the alphabet is. Let's see, A, B, C, D, E, F, G, H, I, J. I knew that. Okay, So if I have horses A through J and I'm looking for the top triples of finishing, well, ABC is the same triple as CBA, but it's a different triple from ABD, right? So I need to divide by the size of the symmetries. So when we were doing the thing with the different letters in the words, we had like A1, A2, A3, whatever. And when we had three things to arrange, we divided by 3 factorial. We divided by 3 times 2 times 1. So if I've got 3 things to arrange, I'm going to divide by 3 times 2 times 1. And this is really kind of the answer I'm looking for. I'll show you an alternate form of both of these answers that I would be looking for or would accept. But I really prefer something like this as opposed to doing whatever 720 divided by 6 would be, which 720 divided by 6 should be 120, right? So, that's a fine answer. There's nothing wrong with it. It's just this really shows me where the numbers are coming from. This is a number. So let's try to formalize. I can do this, but as the numbers get bigger, it might be a little easier if I had some. Might be better if I had some way to organize this information. So in general, the number of permutations is going to be PNR, and that's going to be n factorial over n minus r factorial. And why is that? Because when I'm doing this selection here, let's just do it for the 10 horses. When I'm doing this selection here, if all I care about is the top 3 medals, I don't care about medals 4 through 10, right? So if the horses finish in the order A, B, C, and then D through J, that's the same top finishing triple as A, B, C, and then D through J, except with the last 2 switched. All right, I don't care about those last few finishing. So the number of ways for all 10 horses to finish is going to be 10 factorial, but then I divide out by the horses that I don't care about, namely the other 7. So where this is 10 times 9 times 8, this is actually 10 factorial over 7 factorial. So let's just check that. So for part A again, this is 10 factorial. Well, let me write it. P10(7). This is 10 factorial over 10 minus 7 factorial. That is, 10 times 9 times 8 times, okay, I go 7 all the way down. That's 10 times 9 times 8 times 7 factorial. Oh dear. I've got a typo here. I'm choosing the top 3, not choosing the top 7. So this should be 10 minus 3, and that's where I got my 7. So this should be P10(3), 10 minus 3 factorial. 10 times 9 times 8 times 7 factorial. 10 minus 3 is 7, divided by 7 factorial. And this is 10 times 9 times 8, which is the answer that I got for part A. All right? So we reasoned through this using just the very first rule we learned in this chapter, right, which was the multiplication rule. But now we're checking it does line up with our intuition for the symmetry rule, if we have this really nice thing where we're just picking things in order. Okay, now let's look at the number of combinations. So the number of combinations is something which you might see written as CNR. I don't like that notation for a number of reasons. But I'm gonna be using this notation, n choose r. This is sometimes called the binomial coefficient. Or n choose r. That's the name of this little symbol. It's like wide parentheses around a fraction, except there's no fraction bar, so that's how that looks. And this is just going to be PNR, but we're going to divide by, so this would be, PNR is the number of ways to order our objects, but we're going to divide by the order of those objects, right? just like we did here. I had the number of ways that the top three horses could finish in order, and then I divided out by that order. Because it's like, 3 times 2 times 1. It's like I would have 3 times 2 times 1 identical lists of the top order. And another way to see this, if I plug in this PNR formula, is n factorial over r factorial n minus r factorial. And this is what we call n choose r, or the number of ways to choose r objects from n. If I'm just choosing objects and not necessarily putting them in order, then I'm probably going to be using combinations. So if I'm saying, well, I've got 10 books and I can fit 3 in my book bag for my road trip, which 3 do I pick? It doesn't matter the order that I pick those books. I either have them or I don't. That's different from, I'm picking positions for a team, and depending on the order that the team is lined up, this guy might be a great catcher, but he's playing pitcher, and this guy might be a great pitcher, but he's playing catcher, and that would be maybe non-optimal. So the order doesn't matter with combinations. Let's check how B works if I plug in this formula. So n choose r, this is 10 choose 3. Well, I'm looking for 10 factorial over 3 factorial 10 minus 3 factorial. And we remember 10 factorial over 10 minus 3 factorial. This was 10 times 9 times 8 times 7 factorial. This is 3 factorial. This is 7 factorial again. So I've got 10 times 9 times 8 over 3 factorial, and that's exactly what I had last time. So hopefully this is just showing you the absolute basics for combinations and permutations. So it might merit, just to remind you, I just realized I'm throwing around factorial. Remember, n factorial is n times n minus 1 times n minus 2 times ... times 3 times 2 times 1. And we also have that 0 factorial equals 1. This one's troublesome for some people. And we covered this earlier in the semester, but in case you missed that, or in case you've forgotten about that, that's how that works. So I'll let you kind of look at that for a second. I'm taking a drink of coffee. Let's do a couple of simple examples involving permutations and combinations. So let me start by I'll put those formulas back up here. So I'm going to write ordered. That's PNR, which is n factorial over n minus r factorial. And then unordered, that's going to be n choose r, which is n factorial over r factorial n minus r factorial. That n minus r is in parentheses. So just quick examples. Do sort of 2 quick examples. Let's see. I have. We've already done 10. Let's do a different number. I have 20 books, and I can bring exactly 5 on a trip. How many different pentuples of books could I bring? So take just a minute, try to think about, is this an ordered question or an unordered question? I have 20 books and I can bring exactly 5 on a trip. How many different pentuples of books could I bring? So we already discussed this, but I didn't write it down earlier. So if I'm either bringing the book or not, I don't care what the order is. So it's going to be 20 choose 5. And I don't need to write out anything more than that because the numbers are going to get hilariously large. And I definitely don't need you computing this by hand. And even the numbers that maybe like Mathematica or something would spit out probably won't mean a whole lot to us. Okay? They're just going to be big numbers, so I don't really care. I prefer you to answer like this, or if you want to, you could write, 20 factorial over 5 factorial, 15 factorial. You could simplify it down, but really this is what I'm looking for. Okay, another example. So I have what? Let's just do the playlist. I have 15 favorite songs. How many playlists could I make with 10 of them? Or 10 of those songs on it. Okay, so again, we already discussed this, but think about a playlist. If I'm playing from top to bottom, so it's not just on shuffle. A playlist, does the order matter? And hopefully you can see the answer is yes. The order matters. If I'm trying to shape the mood at a party, it's gonna maybe start with some energy and change to a different energy. Either it's gonna start kind of mellow as people are arriving, and then eventually crank up to like dancier stuff, or I don't know what kind of music you like or you play at your parties. But if you're trying to shape what's happening, the order matters. So we're going to be using PNR, and all that I want from you here is P1510. Okay, you could compute that, but I'm not really going to worry about it for now. Okay. So yeah, P1510, you could write this down. This is going to be 15 factorial over the quantity 15 minus 10 factorial, so it would be 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6. Cool. I don't care. Okay? So this is sufficient. All right, let's do something a little bit more interesting. So most of what you've seen so far is pretty canned. So let's do something a little bit more interesting. So prove that n choose r is equal to n choose n minus r. So I'm going to give you two different proofs, but I want you to think about this for a moment first. Okay, so proof number one is the non-thinking proof. We just write down n choose r. We write n factorial over r factorial n minus r factorial. And we write down what this is. Well, this is n choose n minus r is n factorial n minus r factorial n minus r factorial. And we notice n minus r is just r. So these two are equal. All right, we just showed that the left-hand side equaled the right-hand side. That's true. I just used the formula and I checked that that was true. Let me give you a second proof. And this is a proof which I'm going to say is by double counting. And some people might disagree and say this is too simple to be called double counting. That's fine. People are entitled to their opinions. I think this is one of the simplest ways that we can exhibit double counting. The left-hand side is the number of ways to choose R objects from N, which is equal to the number of ways to not choose n minus r objects from n. But guess what? That's equal to the right-hand side. And you might say, wait a minute. How is that equal to the right-hand side? No, that's not the way to not choose. That's the way to choose n minus r objects. But every time that I choose an object, It's the same as not choosing the other objects. So every time that I choose n minus r things to not be chosen, that's the same as not choosing r things to be chosen, or vice versa. Basically, choosing r things from n is the same as not choosing n minus r things from n. If you have 4 best friends and you want to go on a road trip and you only have 4 seats in your car, then you have to pick your favorite 3 best friends to go with. But probably what you're going to do is pick your least favorite of those 4. And you're going to think, well, who's the most annoying? Right? So if I have, right here, I've got a total of 4 objects and I want to pick 3. One way to do that is to select my favorite 3. Another way to do that is just to say, well, I can live without that one. Okay? So that was a simple example of double counting, and that can be applied in a lot of different scenarios, but we've just applied it here to combinations. So again, big ideas. Permutations are ordered lists, so ordered list of R objects chosen from N, and that's the formula. Combinations are unordered lists, so it's the number of ways to choose R objects from N, where the order does not matter. That's all we have for basic counting. I hope you're having the best day ever.